to write a var_char2 declaration, a constrained declaration, stop and ask yourself, what kind of assumption am I making here? Is it really possible to say it's never going to be bigger than 300? Or am I always going to declare my variables to be like 32,767 because that's the maximum length allowed in PL/SQL now? Well, instead of doing that, or instead of even writing a comment explaining the way you declared things, put your explanation into the subtype itself. Here's an example. So I need to declare a variable to hold the full name of an employee, and as you've seen in multiple of my examples, full name is defined as last comma first. So I can't use %type against the column in the database. So what do I do instead? I do a var_char2 100. That can lead to all sorts of problems, as I've already mentioned. My second variable is called lBigString. I need to declare a variable that holds the largest size possible string in PL/SQL. Well, I look it up in the documentation. It says that it's 32,767. So I'll do that. But now I've hard-coded the assumption that Oracle's never going to raise that limit, which it might well do. So instead of doing these kinds of things, hard-coding an application limit or a limit you hope will be valid, hard-coding a PL/SQL limit that you think might never change, let's do something like this. I'm going to declare the full name variable to be of type employees RP, the rules package, dot full name. I'll declare my big string to be of type PL/SQL limits dot max var_char2, maximum var_char2 possible. Now notice this code tells its own story. My full name variable is of type full name. What is a full name type? Well, I don't really know as the developer, the application developer, and I don't really care. I just know that that's the appropriate type to use. If I want to, I can go to the package and look it up, and we will take a look in just a moment. But I don't really need to do that. All I need to do is follow the predefined types provided for me by the folks who set up the application environment, the framework. Instead of hard-coding a limit of var_char2 32K, I'll go to my PL/SQL limits package, pick out the max var_char2, and basically say in my code, I want the largest size possible string, but I don't hard-code it. So you can see that once again, I've replaced specific implementations, hard codings, exposures of the way I'm doing things with named elements that describe what they represent and hide the details. So inside my full names package, or my employee rules package, I can declare a subtype called full name T. It's a var_char2 10,000, 1,000, 5,000. It doesn't really matter. The most important thing is it's defined once and it's referenced multiple times. And therefore, if I ever need to change the size of my full name, let's say 10,000 isn't big enough, I need to change it to 20,000. I recompile my package spec. All the programs that reference the package and certainly this type have to be recompiled, but the code itself doesn't have to change. Same thing with PL/SQL limits. I declare this package. I have a max var_char2 set to 32,767. A db max var_char2, that's a max of 4,000. And a whole bunch of other stuff. You can take a look at this package when you have some time if you decide to use it. Once I've defined this package, I can then say, well, I just need the biggest string possible, please. Don't bother me with the details. Don't hard code the limit. And then if Oracle ever changes it, let's say to 4 gig or 64K, then I can just put the new value here, recompile the package spec. None of my application code needs to change. All it has to do is be recompiled. So subtypes, and the benefits of subtypes are really the same as %type. It's something you're familiar with. You get on recompilation, it updates you to the new definition. The difference here is that you can create named elements that tell a story about what that variable holds and are application specific. I'd also mention the value of using subtypes for complex collection structures. Let's take a look at String Tracker 3. Now I'm not going to get into all the details here. What you want to do, if you want to explore it in great detail, is to check out the collections series of lessons and multi-level collections in particular, or nested collections. Now what I've done here is define a very complex structure. I've got a list of lists. Each list is a record. I'm sorry, the list of records, my apologies, list of lists is a collection in which each element of the collection is a record. Each record has two elements, or two fields, case sensitive and list of values. The list of values is a collection itself, a table of who cares, which is a Boolean indexed by value string. Now notice I've got a lot of subtypes. Actually, you can only see some of them here. Some of them are in the package specification. So here's my subtype max varchar2. Here's my subtype list name value string. Here are some examples of nested subtypes. This subtype is defined on another subtype. So they're basically just alternative names for strings. But the key thing here is not that I'm hiding the data type, but I'm explaining what these things are used for. So in my package body, I say index by list name. I'm saying literally that the indexing scheme for this list of lists is the name of the list. The indexing scheme for this list of used elements is the value string. And the contents of my collection is who cares, a Boolean. And the reason I say who cares is that in the context of my algorithm, in the code that I'm writing, the value inside this collection doesn't matter. I'm literally documenting that it doesn't matter what's in the collection. The thing that matters is that I'm indexing by the value string. Now again, the point here is not to understand this code, but let's compare it to what it would look like if I didn't use subtypes. So I would put varchar2 100 here, varchar2 100 here, or whatever I decided the correct size is. I'd replace this with Booleans. And now, when I look at this code, I don't know what's going on. What is it indexing by? And I would have to add a comment saying, index is by list name. So I lose information here. I hard code the length, the limit. I have to add a comment explaining what the heck I'm doing, and all of this is completely unnecessary. All I have to do is create a subtype and use my subtypes in my code. It's indexed by the list name. It's indexed by the value string. So my code tells its own story. And I think this is one of the most important benefits of using subtypes, improving the self-documentation of your code, avoiding the need for comments. Let your code tell its own story. Draw some conclusions. Declarations offer a danger of hard coding from both the standpoint of the data type itself and any constraint on that type. Declaring variables is something we take for granted. It's the most basic part of writing your program, just declare a bunch of variables. But even inside that declaration section, you can introduce enormous problems in your code. Assume over time that everything is going to change. Your data types of your columns could change. The lengths of the columns could change. The rules that these columns are based on can change. And apply the same single point of definition principle, the spatification, that you would apply to rules and to literal values to your declarations. If you can find an existing column or table that your variable is going to be based on, the values that are populating in that variable are based on, use %type and %row type to declare them. Anchor back to those database elements. That's always the preferred method. If you cannot find an element in the database in a table to anchor back to, then fall back on subtypes to define application-specific data types, PL/SQL limits, etc. Anything that you can't locate within your database tables, use subtype to create your data type and then reference that data type throughout. Next steps. Download the demo zip. Try out all the various scripts I showed you in this presentation. Make sure you understand the downsides of hard-coded declarations. Make sure you see the benefits of %type and %row type, and especially of subtypes, and start using them in your code. Self-document those declarations. And then watch the other lessons on how to remove various kinds of hard coding from your programs, removing literals, removing rules and formulas, or hiding rules and formulas. And I encourage you to especially check out hiding the SQL statements in your application. I argue that all SQL statements you will ever write are hard codings. In fact, the worst kind of hard coding, and require a lot of attention, diligence, and hiding, which is not what very many of us think about when we think about SQL and PL/SQL. So check that one out. I hope this lesson was useful to you. Happy PL/SQL coding into the future. Greetings and welcome to the PL/SQL channel, a series of video trainings on the Oracle PL/SQL language. My name is Stephen Feuerstein, and I'm a PL/SQL developer, just like you. This lesson is part of my series on Say Goodbye to Hard Coding, a series of lessons that talk about what hard coding consists of, and then how you can get rid of it. The focus of this lesson is hide business rules and formulas. quick reminders. If you haven't already done so, go to toadworld.com/sf, my initials, also known as PL/SQL Obsession, where you can access all of the code that I'll be demonstrating in this lesson and PowerPoints to support these trainings as well, and many other resources for PL/SQL developers. Also, make sure you're comfortable with the material covered in the previous lessons in this series. Very importantly, overall introduction and concepts. What is hard coding? Why is it bad? Developing a sensitivity to identifying various kinds of hard coding, and hiding magic values, the most simple and most common example of literals of hard coding in your application. So what we're talking about in this lesson is hiding rules and formulas. Now, generally speaking, the rules and formulas in your application are much more critical than hard-coded literal values because they really determine a lot of the behavior of your application. And all too often, we tend to just write those rules, expose the implementations of those rules over and over again in the application, which is really a bad idea because what we know about rules and formulas in our applications is that they are always going to be changing. And almost always, they get more complex. Very rarely will you ever run into a situation where your users come to you and say, you know that really complicated formula we've been using for years? We want to simplify it. It's unlikely to happen. It does happen, but more than likely, what happens is that the rules get more and more complex over time. So what do you need to do about this? Well, the first thing is to learn to recognize when you're writing a rule or a formula in your application code. You'd think that would be pretty obvious, but sometimes, especially when the rules are simple, we don't notice that we're doing it, and it creeps into our code incrementally. And then we end up with a problem because we can't even find all the places where those rules might occur. Once you recognize that you're doing it, the solution is pretty simple. Hide the logic behind functions. Don't expose it. Simply call a program that returns the result of applying the rule. So let's take a look at this piece of code and identify all the different places where rules occur in the logic. This is a variation on the code that I showed as part of the Introduction and Concepts lesson. And what I suggest you do is pause the video now, take a look at this code, find all the places where you think a rule or a business rule or a formula occurs, and then continue. And I'll show you what I think is going on. Okay, here's what I think is going on from the standpoint of rules and formulas. First of all, basically what we've got at the top of the program is a little reminder that the way we construct the full name of an employee is last comma first. Clearly, that is a rule. That's how we work with and display names. So that's a hard coding of the business rule right there in the comment. More importantly, we have the business rule exposed in the select statement, last comma first. And again, this is a very simple rule. It's very easy to write, so why not just write it? Well, because the construction of the full name might change over time. That's not all. Then inside my cursor for loop, I say, if the salary is greater than 1 million, well, that means clearly, by looking at the code, I can say clearly, that means it must be the CEO. So do an adjustment of compensation for the CEO, passing in the salary value. If the salary is between 500,000 and 1 million, well, that must be an executive, a non-CEO executive, so we'll adjust their compensation. Otherwise, we'll adjust the compensation for everybody else. Well, each one of these little Boolean expressions are also business rules. We're saying that this is what defines the CEO. This is what defines an executive. So again, these are exposures of these rules. If we write them more than once, it can be very difficult to track them down. And I'm sure you also realize that having this 1 million repeated over and over again and the 500,000, those are all examples of hard-coded literal values that should be hidden away because, of course, those ranges and those limits might change. So, 3 formulas, business rules, last comma first, what makes the salary level indicate a CEO, what makes the salary level indicate an executive. And so the main thing is to take a look at this code, to ask yourself, did I find all of those? And if not, ask yourself, why not? And then perhaps go back to some of your own code. You can even pause the video and do it right now. Pick up one of your own programs and look through it and see if you can find examples where you've unknowingly exposed and had multiple instances of the same rule. So that's the biggest challenge when it comes to doing this kind of reduction of hard coding, even recognizing that you're doing it. And you can see the same example of the code in hardcoding_rules, which is available in my demo zip file downloadable from PL/SQL Obsession. We'll come back to this file later when we talk about what this code should look like. So the bottom line is never trust a rule, never trust a formula to stay the same. And what I'd like to do is drive home how critical that is and how you can never trust a rule by giving you an example from the world of Oracle. So Oracle offers a utility function called getTime and getCPUTime in the dbmesh utility package. And these programs can be used to calculate elapsed time of your own programs down to the 100th of a second, which is nice, better than sysdate, which calculates down to the second. So here's an example of how I might use getTime. I call the function before I start running my code, and I store that value. Then I run my application code that I want to measure. Then I call dbmesh utility getTime again and subtract the start time. So it's end minus start gives me the number of hundreds of seconds that have elapsed. Let's take a look. So here's my getTime script. Basically what you just saw before. Get my start time, and I'll display it. Call the dbmesh utility getTime 1,000,000 times. Then call getTime again. That's my end time. Subtract end minus start. Obviously, a very simple formula. I run my code. It shows me that it took about 0.43 seconds, 43 hundredths of a second, to calculate the time it took to run getTime 1,000,000 times. So that's the starting time, that's the ending time, and these are the number of hundredths of seconds that have elapsed since an arbitrary point of time on the computer. So that's it. Great. I can now calculate elapsed time down to the 100th of a second. Well, unfortunately, it turns out that even though that's a trivial formula and it seems very obvious, it's actually wrong in that sometimes this formula can give you the wrong answer. How, you might wonder, is that possible? Well, these numbers, these hundreds of seconds increment get larger and larger until they reach an operating system limit. And it can vary based on the operating system. And when it hits that limit, it doesn't raise an error. It just says, okay, I've reached the largest size possible for my number. I'm going to loop around back to 0 and start counting again. So if I call getTime right before it loops, when I call getTime for my start time, right before it hits the limit and loops back to 0, then when I call getTime later, quite likely, unless it's a very long-running program, I'll end up with an end time that is much smaller than my start time, and the end result will be a negative elapsed time, which is not correct. It turns out that if you want to write a foolproof formula that always gives you the right answer, it needs to be something like this. Take the end time minus the start time, add a really big number to it, and mod by that number. And this will always guarantee that I get a positive elapsed time. Wow. Now, when I train people about getTime and I show them this, if I just show them this, likely people will start to write scripts that look like this. Declare a variable, call start time, run my code, call getTime again, and do the subtraction. It's so simple. And yet you could sometimes, rarely, but sometimes end up with the wrong answer. Instead, what you want to do is hide the calls to these programs. Hide the call to getTime, hide the call to the formula, so that I don't have to worry about these complexities. So for example, if I was using my timer package, which is also available in the demo zip, I would simply say start the timer, run my code, and show the elapsed time. And I can put a little message, call getTime 1,000,000 times. So I could convert it to this. I don't have to declare any local variables, run my code. Whoops. I need one of those local variables. And then it shows me the amount of time. So there's an example of the exposed way of doing things. Let's pull that file back up. And the encapsulated format. Let's just save it here for us for later. So in the first case, I know about the mechanics of getTime. I've studied it. I know about the formula, and I write all of this code, including the exposure of the formula. And that can lead to problems. Sometimes I might get the wrong answer. Now, obviously, with elapsed time calculations, if you got the wrong answer, it doesn't matter. You can run it again, and likely it wouldn't happen to you again or ever. Of course, with your real business rules and formulas, you need to make sure it's right all the time. And the way I make sure it's right, and the way I improve my productivity and the quality of my code, is I create a utility that puts all the details inside the package. And all the package does is expose a very simple API, procedures and functions, start my timer, show my elapsed time, and all the details are hidden away inside. So as a developer, as a user of the formula, I can be much more productive. I don't have to know about all the internal details, how things are done. And also, I don't hard code the formula. So that's a very trivial, simple example of something from Oracle that I hope will demonstrate the fact that you can never trust a rule, never trust a formula to stay the same. They will get complicated, bugs will be fixed, many different reasons that things will change. Hide the formula behind a program. In this case, I'm actually hiding it behind a procedure. Usually, you'd hide it behind a function that returns that value. But I only really need to see it, so I just said show the elapsed time. Hide the implementation, and then I simply call my program. And if it turns out that this implementation is wrong, that I need to change it, I change it in one place. And then everybody who uses my SF timer package is able to benefit from the fix without changing their code at all. Same basic idea. Single point of definition. This is my spodification of the original implementation, which exposes the rule. And if you don't know what I mean by spod, single point of definition, then you definitely should watch my introduction and overall concepts for hard coding. Okay, so there's an example that hopefully drives home that point. Never trust a rule. So getting rid of hard-coded rules, generally speaking, quite a straightforward process. First of all, identify the problem, identify the exposure of the rule. Then create a function, hopefully in a package. Copy the rule contents, the data, the code to the function. Make sure the name you choose for the function accurately expresses the rule. This is critical. If you come up with a bad name, people won't be able to identify the correct function that correlates to the rule. And then take out the hard-coded logic and replace it with a call to the function. And then what you want to do is make sure that the body of the function has no global references. Pass everything through the parameter list. So as you move things out of your local code and move it into a function, you need to identify all the inputs that have to come into that function to execute the rule without having those global references. Let's go back to my hard coding rules file. So this is what I started out with. Here's my exposed last comma first. Here's my exposed rule for CEO level compensation, executive level compensations. Here's what it looks like after my first round of changes. I have a separate package called employees rules package, and it has all the full name information in it. So I simply call the full name function, pass in first name and last name, and it returns the full name for me. So the formula is hidden away. Then I create a new package, comp analysis package, and I put in a CEO salary level function. Is this the CEO salary level, returning true or false? I pass in the salary, it returns whether or not it is in that level. Same thing for executive salary level, so hiding away the formula. And let's take a look at the employee rules package. So I declare a function called full name, pass in, oh look at this, pass in last comma first. I got it wrong. Let's go back and fix that. Okay, first space, last comma first, and it returns the full name, and we can even look at the function body, and it's actually kind of fancy. I tell it we can use first last or last comma first, and you can pass in a Boolean determining which one you want to use. One of the advantages of having a single function that hides all the details is you can afford the time to, quote unquote, make it fancy, put in some bells and whistles, add in some flexibility. Whether or not you want it is a separate question. But my single function has all the information about how to construct the full name. So I go back to my original code. I pull out the hard-coded references. These are my inputs that determine my full name, and I pass them as arguments to my function. And that's what you would do over and over again with every single rule that you find. And just as a final step here, notice that I have my comp analysis package. I created these different Boolean functions to return true or false. But I have these separate schema level adjust compensation for CEO, for executive, etc. programs. These should be taken out, I think, as separate schema level programs and put into the same package. So in my last refactoring or modification, I've taken those schema level procedures and I've moved them inside the package. So this one package, my comp analysis package, collects together all the related functionality for compensation analysis and changes. And therefore, there's one place to go to maintain all of this stuff, which will make it much easier to work with this application code in the future. But certainly in the context of this lesson, the main thing is get this hard coding out, get these rules out, put them inside their own functions. Conclusions. Generally speaking, when it comes to refactoring or getting rid of your exposure and hard coding of rules and formulas, the hardest part is developing the sensitivity to recognize when you are exposing that rule or formula. Sometimes, especially with the simplest ones, they sneak in and we don't even realize it. Once you've recognized you've done it or are about to do it, the resolution is straightforward. You create the function, you move the body of the code or the rule into that function and call the function. So the bottom line is be wary of assumptions. Your rules will change. They will get more complicated. Hiding them is your best form of programmer's insurance. If you don't hide them, you will have misery in the future as you go back and try to find all the instances of that formula and get rid of all the bugs that would result if you don't fix every single one. Next steps. We'll download the demo zip from PL/SQL Obsession if you have not already done that. Take a look at the hard coding files. Try out and the get time script. Try out what I just showed you. Make sure you understand the benefits gained by hiding and how you go about doing it. And then watch the other hard coding oriented lessons. And the one I would definitely recommend most of all, and the least obvious, is the lesson on hard coding and removing the hard coding of SQL statements. I argue that all SQL statements are hard codings and they're really critical to get rid of, which most people don't recognize or accept. So take a look at that one. I hope this lesson was useful to you, and happy PL/SQL coding.